Hello. So I'm going to use Gemini 2.5 Pro, asking it as a theorem prover. Can you prove Euler formula, that is e to the power ix equals to cos x plus I sin x? So let's listen.
Okay, let's prove Euler's formula, which states, there are several ways to prove this, but one of the most common and intuitive methods uses Taylor series expansions. What you need to know beforehand, the building blocks. 1. Taylor series, or Maclaurin series, which is a Taylor series centered at 0. Any infinitely differentiable function f of x can often be represented as an infinite sum of its derivatives at a single point. The Maclaurin series for a function f of x is 2. Maclaurin series for e caret z, cos x, and sin x. For e caret z, where z can be a complex number. For cos x, for sin.
So Maclaurin series is basically a Taylor series centered at 0. So it is given by function of x equals to function of 0 plus f prime, that is first order differentiation, f prime 0 times x plus f double prime 0 divided by 2 factorial times x squared, that is second order differentiation, plus f3 0 divided by 3 factorial x cube plus dot dot dot. So basically that is the Maclaurin series. So Maclaurin series for e to the power z cos x and sin x. So e to the power z equals to 1 plus z plus z squared divided by 2 factorial plus z cubed by 3 factorial, so on and so forth. Same for cos of x is 1 minus x squared. Same for sin of x equals to x minus x cubed by 3 factorial plus x cubed by factorial. And for I, the powers of the imaginary unit, of course, I power 0 equals to 1, I to the power 1 equals to I square equals to minus 1, I cube equals to I square times I equals to minus I, and I to the power 4 equals to I square whole square 1. So it is a period of 4. I to the power 5 equals to I to the power 4 times I equals to I. So the pattern repeats. So as you can see, it is already the theorem. It is already shaping up. So start with the Taylor series for e to the power z and substitute z equals to ix. So series for e to the power z. Now let z equal to ix. So e to the power ix equals to 1 plus ix whole square by 2 factorial, and simplify the terms using the power of I. So it goes on. So it looks like pretty good solution, pretty good proof. Substituting cos of x and sin of x back into the equation, it gives e to the power ix equals to cos x plus I sin x. Okay, it also has given another way of proof involving differentiation. So let function of x equals to cos of x plus I sin x divided by e to the power ix. So if the numerator and denominator are equal, then we want to show that function of x equals to 1. So differentiate with respect to x, f prime x. So ddx of numerator times denominator minus numerator times ddx of denominator divided by denominator whole square. Factor out e to the power ix from the numerator, f prime x. Then we come into this, simplify the numerator because I square equals to minus 1, which eventually gives f prime x equals to 0. That means fx must be a constant. If the derivative of a function is 0, follow all of x, then the function must be a constant. So function of x equals to c for some constant c. So next step 5, find the value of c by evaluating function of x at a convenient point like x equals to 0. So function of 0 equals to cos of 0 plus I sine of 0, which gives eventually function of 0 equals to 1. So the constant c equals to 1 because it will be 1 at every point. So the conclusion, sin fx equals to c and c equals to 1, we have f equals to 1, which means cos x plus I sin x divided by e to the power ix equals to 1. Multiplying both sides by I e to the power x gives cos x plus I sin